Hi, welcome to 8th lecture in the series of audio and speech signal processing using MATLAB. You can visit us at for the theoretical version of the lecture at www.jcbrolabs.org. You can also download the MATLAB source code of this lecture from that website. In this video, we'll talk about short-term autocorrelation and how to find the short-term autocorrelation of a sequence and how to use the second coefficient of short-term autocorrelation or the or coefficient of autocorrelation at lag 1 in order to remove the silence from a speech signal. So let's first go through the theoretical part of the autocorrelation function. We'll talk about autocorrelation, and prior to going to the formula of the autocorrelation, let's have a small discussion about why we use autocorrelation. So autocorrelation is derived from the cross correlation function. So mainly cross correlation function is used to find the similarity between or among two signals or the two sequences, and if these two sequences are different, then that is known as the cross correlation. And if we find the similarity between the same sequence at different lags, then that is known as the autocorrelation. So we can say this autocorrelation refers to the case of having only one sequence for correlation. So this correlation is generally provided with multiplying one sequence with the shifted version of the another sequence, and then adding them together all the terms which we are getting. So if we go for the formula for autocorrelation, then this autocorrelation formula can be given as Rxx, which gives the autocorrelation between x and x is equals to summation of m equals to minus infinite to plus infinite, and then x of m into x of m plus k. So exactly what we are doing, suppose this k value is equals to 0. That means when k is 0, then this is also xm and this is also xm. So this will be termed as the 0th coefficient. Then this Rxx will be 0th coefficient of the autocorrelation. And for that case, what we are doing, we are just multiplying the two sequences. When this is 0, this will termed as xm, and both these are will multiply together, and then we will add the sequence from minus infinity to infinity. That includes like the length of the sequence. Now if we say k equals to 1, and it will be termed as Rxx at 1, that means xm and then xm plus 1. So this will shift to x of m plus 1. That means original sequence is multiplied with the same sequence shifted by one sample. So there is a one lag in the second sequence, and then we multiplied all the terms and then adds them. Similarly, if for k equals to 2, it will be m plus 2, and the second coefficient will be termed as Rxx2, and that will be termed as the second coefficient of autocorrelation, as when the input sequence is multiplied with the another sequence shifted by two samples and then added them together. So this gives the general formula for autocorrelation function. But as we have discussed earlier, most of the signal processor formulas are for stationary signals, but generally our speech signal is not a stationary one. So what we do, we apply a kind of windows to get the short duration of the sequence, and if we calculate the autocorrelation function for that short duration, then that will be known as short-term autocorrelation. So we will now write the function for the short-term autocorrelation sequence. It is quite easy for writing a short-term autocorrelation. We apply a window function there for say Rxx, and k is equals to m equals to minus infinity to infinity, and then x of m into w of n minus m into s of k plus m into w of n minus k plus m. So this formula is similar to the previous one. The only difference is this extra term w of n minus 1 and this w of n minus m. So this w of n minus m is the window, as we discussed in our last lecture, of short term energy, and we can say this we can write this complete signal as x w of n is equals to s of m into w of n minus m. So this is this can be termed as the windowed function. The original function, this is x, the original function has been multiplied with the size of the window, and the remaining signal which we get after applying the window, that will goes here. So in our case, as we discussed, we will be using the rectangular window. So if our signal is like this, so in a case of rectangular window we are applying, so with zero overlapping, this complete signal will be termed as x of m, and then we will be taking this separate signal out of this whole signal, and then we will apply the short term autocorrelation analysis on it. So we will use the same formula for applying for writing the MATLAB code for short term analysis. Further, as our video is focused towards the silence removal, so we will be considering only the second coefficient, or the rxx1 value for calculating, for using this coefficient value in order to remove the silence. So we will get this coefficient when we provide a lag of 1. So now let's do a MATLAB program for writing the same in MATLAB. Open MATLAB and write a function for the same. Now, as usual, first we'll write we'll read the MATLAB command, or let's say first go to the folder where our all files are lying. So let's clear all CLC, and that's it. Yeah. So now, and close all. So now first read the data of the sound file, which is audio read, and I think intro.wma, and let's normalize the data. Actually maximum of data. So now we get data normalized, and let's see how the data or the speech sound looks like. So this is the signal. Okay, now let's do framing. So first we define the duration. So we'll do framing for 25. We'll divide this complete signal into 25 millisecond duration, and this framing is a kind, you can think of it like a rectangular window of this much of time duration. So both will give the same result. So let's call framing, and it takes data, comma sampling frequency, comma f. So we'll get 345 frames, and each frame size is 1103 of length CLC. Now as we discussed in just case for calculating the autocorrelation function, so there are two ways. MATLAB also provide the autocorrelation function, but that is normalized, and the first coefficient, that is zero lag, is always 1, because that is the maximum. and the second coefficient which is at lag 1 is also very high, and that doesn't provides us much useful information in order to remove the silence. So what we will do, we will write our own function for finding this autocorrelation, and then we will extract the first coefficient of the autocorrelation function at lag 1. So let's first have a look of autocorrelation looks like frame. So we are taking the 110th frame, and let's see how this frames looks like. Let's plot the signal. So this is clearly a kind of periodic sequence, and this is obviously a voiced part. So we can provide autocorrelate of this t, and then we need to provide the lag. So if it is a sinusoidal kind of fashion, we will get this kind of signal, and from that we can also find the pitch of the signal, and we'll discuss about it in upcoming videos. So now let's write the same code in MATLAB. So first of all, because we want to do this autocorrelation for all the frames, let's we'll write a code for single frame, and then we will extend it to for all the frames. So we have t in which frame 110 was there, and now we'll write a code, because this was simply the multiplication and addition of all the sequences. So we'll define like sum of 1 is equals to 0, and then for I equals to 0 to length of t minus 1. So we are going from frame length minus 1 time, and then we are making sum 0 for each iteration, and then again I equals to 1 to t. So particular this portion, this command is providing the lag to the sequence, and this command is going for the complete length of the data. Okay, so because if I will be 1, lag will be 1, I will be 0, lag will be 0, I will be 2, lag will be 2. So this is used for that purpose only. Now I will simply s equals to, okay, we done a mistake. Okay, so cross it, and actually this needs to be c j, otherwise both the coefficients are same, and then s equals to t of j into t of j plus 1, and then we have already defined sum of 1 equals to sum of 1 plus s, and then and then we'll keep on accumulating this sum and autocorrelation sequence, that is AC equals to I plus 1 equals to sum of 1, and again for each iteration when it will go again into iteration, will make sum 1 equals to 0, and then so it is saying attempting to access. Okay, let's say we are wrong. Okay, so we did a wrong command, we added plus 1 here, so it's not plus 1, it's plus I. So let's do this one. You can get this code. So in AC command we will get the autocorrelation function. So if we plot this autocorrelation function in STEM, we got the same answer as that of the original autocorrelation function from MATLAB command. Let's make it figure auto RR of AC. It will for 20 lakh by default, but we want to go from autocorrelation of T into length of T minus 1. So these both autocorrelation functions are same from MATLAB built-in command and from our own code. So that means we are right in calculating the autocorrelation function, and then we will be using this this AC variable was containing the autocorrelation sequence of the code which we write. So we will be using this second coefficient in order to uh, make use of it in order to remove the silence from the SP signal, because this one is at 0th lag and it is always a kind of the same sequence multiplying it, and it becomes a kind of energy of the signal. So we'll concentrate on this one, the second portion. So now let's move forward, and we have written code. So the same code we iterated for complete duration of the complete duration of the frames, and we will keep on storing this second coefficient of this autocorrelation function in ST short-term autocorrelation sequence. Because so we'll get this STAC function, STAC variable, and it contains the second point of the autocorrelation function for all the values. Now, in order to make it generalized, what we do, we further make it a normalized STAC by its maximum value, and then let's see how this STAC looks like. So it has some zero value, nearly zero value for some of the frames, and high value for more of the frames. So this zero or nearly zero values corresponds to the noise of the system or noise of the signal or the silence portion of the signals. So we can make use of it in order to remove the silence. So again, as we discussed previously, first of all we will write the same code as we did for short-term energy in order to plot both the signals at the same time. So now if we plot, we can plot the original signal and the short-term autocorrelation on the same plot. And it looks like this one. This red curve shows the short-term autocorrelation, and this blue curve shows the original wave. So where there is a sound burst, the autocorrelation second coefficient is high, and for noise portion it is really very low. We can use this method or this property of it. Now again, as we have done in previous lectures, the rest of the thing are same. We'll find only those IDs for which STAC vary less, 0.01, and then first we will get only those frames which have higher than that of amplitude, and then we will reconstruct the data. And now we can plot both the signals at the same, the original signal and the reconstructed data. So this green curve shows the reconstructed and this blue was the original signal. So it is already showing that most of the silence portions have been removed from it. So We can verify it by playing the sound, by playing this reconstructed data. You can also hear the same thing, and you will find that silence portions have been removed from the entire speech. And further, we can also, if some of the portions are remaining, we can also adjust this amplitude value for removing those small kind of error or other noise portions as well. So this is the script of this lecture tutorial, and this will be uploaded. This has been uploaded on our website, and you can download this particular source code from that website as well. Let's run it again one more time, and we'll find this is the autocorrelation function and the original sequence, and this is the sound after removing the silence from the speech signal. So I hope from this video you understand how to find the short-term autocorrelation function and how to use this short-term autocorrelation function in order to remove the silence. This autocorrelation also has some other properties, and this is also used in finding the pitch of the waveform, and we will do in upcoming videos. And we will also learn how to remove silence based on the pitch information. So that's it for this video.